Hello everyone, so I'm here today at the University of Warwick at the Marsh Observatory to learn more about the amazing work that Dr. Heather Cegla is embarking on. She's doing research to find out whether there's another Earth-like planet, like where we're living, existing in another solar system. So, Dr. Heather Cegla, in your own words, explain who you are and the research that you're undertaking.
Yeah, thanks. I'm an associate professor and a UKRI Future Leaders Fellow here at the University of Warwick. And my research group is doing, as you said, trying to find planets outside of our solar system and to confirm and characterize those. Because ultimately, in astronomy, one of the big questions we're trying to answer is, are we alone? Is there life outside of the solar system and outside of Earth? And in order to do that, we need to confirm and characterize these alien worlds.
Well, you call them alien worlds. What do you mean by that?
Just worlds other than our own,
Yeah.
really. It's a way to, I find it a nice way to connect with people and really get the imagination going, because we're still really trying to figure out what could be on these other planets.
Okay, so how do you go about looking for other Earth-like planets in another solar system?
Yeah, that's a great question. So for the most part, we are studying the stars, their suns, because they completely outshine the planets. And so there's a couple different ways of confirming and characterizing these planets, but two of the most popular ways is one using transits. So imagine you have like a light bulb and then someone, or like a lamp, and someone walks in front of the lamp, they're going to block some of the brightness from the lamp. And the same thing happens if we have a planet go in front of like its host star. It's going to block out some of that light. And we can measure that dimming. And then from that, we can learn about the size of the planet. And then the other big one is using the Doppler effect. And so imagine like you hear an ambulance going by and you can hear it coming closer and you can hear it going away. The same thing happens if you have a light source and you have that star like coming towards or away from you. We can measure that wobble. And because the star and planet share a common center of mass, they wobble about each other. So our Earth actually, it's orbiting the sun big time, as we all know, but it actually, that presence makes our sun wobble a little bit too. And we're measuring that wobble, and then we can learn about the mass of the planet.
Interesting. So like the standing in front of a light and it blocks it, right? So like if I was to stand in front of a light, I would have a specific measurement. And then in the context of the sun and the earth, you kind of template that measurement in another solar system to see, oh, this measurement suggests that it's an earth. Do you find for the other planets, they have different measurements when they're blocking the sun?
Yeah, definitely. Because if you have a star, like a planet that is bigger, it's going to block more of that light. And so something that is more the size of like Jupiter is going to block a lot more light than something that is as small as the Earth. And then the same for when we're measuring that Doppler effect. So that when we're like hearing that change in frequency from the ambulance or seeing the change in frequency in the light, that depends on the mass of the planet perturbing it. Imagine you're playing tug of war with someone and someone else has a lot more mass. They can tug you a lot more. There's a much bigger gravitational influence. And so more massive planets will make the wobble of the star much bigger. And so when we're trying to find an Earth, it's actually really hard because it's much smaller than like the giant planets that are like close in, like the first ones that were ever found outside our solar system.
Can you get measurements of the sun? Because I'm assuming, does this only work if the star is the same size as our star? Because we're making measurements based on our star and trying to interpret that from the solar system. Are there any other things you need to take in consideration if you're measuring against another star?
Yeah, that's a good question. So the host star will change the properties a fair bit. So if you have a bigger star, then for example, where we would call the habitable zone, the area where you could potentially have liquid water because you're the right sort of Goldilocks temperature away. Then if you have a bigger star, it's hotter, so that zone is further out. And if you have a smaller star, something smaller than our sun, like an M dwarf, they're much cooler. So then where that habitable region is can be much closer into the star. And actually those ones are a little bit easier to find because if you're closer to the star, you're more likely to go in front of it, to transit, and you also have a bigger influence over the gravitational wobble, so you can make your star wobble a bit more as well. And so we're studying their stars, and we need to know their stars in great detail. So learning about our sun is one way to translate that knowledge. But also we just need to characterize the other stars exterior to our solar system in great detail as well, because these are a lot of like differential measurements. So we know the size of the planet because we know something about the size of the star, for example.
So technology is really pivotal in the science field. I'd love to know how you're embracing technology to help advance your research.
Yeah, thanks. There's a few different ways. On one hand, technology is really important from the instrumentation side of things. And so we have to have extremely precise instruments to be able to make these measurements. So we need advances from that side. But then on the other hand, I also use 3D stellar simulations in order to study the stars in greater detail than the instruments currently allow. And then that helps us be able to disentangle these stellar and planetary and also instrumental signals.
Do you use any data and AI to help with your studies?
Yeah, so I mean, we have data from a variety of sources. So the data could be actually going to the telescope and observing the stars or how the planets are influencing the stars. So we have observational data, and then we have simulation data as well that we can use to try to understand how the stars and the planets are interacting. And then we can also use machine learning in order to like try to characterize, for example, the variability on the surface of the star. Because our sun is not homogeneous, it's not sort of smooth and the same everywhere.
Yeah.
There's actually like blemishes or spots on it from regions of variability and convection on the surface. So that's in particular what I study. So imagine you've got like a pot of boiling water and you have that convection. So those hot bubbles rising to the surface, cooling and falling back down. That's the same thing that happens on the surface of our sun.
Yeah.
And we can use 3D simulations to study that. And we can also use machine learning in order to figure out, okay, how is that imprinting on our data? And how do we disentangle the variability from the star from that Doppler wobble that we were talking from the presence of the planet being there?
Well, so much, I mean, technology in essence is being used very much within the research of exoplanets. And there's so many intricacies in terms of the data that you're collecting from like, I guess, wavelengths, speed, and energy, any other sort of data points that you'd be specifically collecting as well.
Yeah, I mean, I think we touched a little bit on trying to measure the size and the mass. And so together that allows us to characterize the density. So we can say something about whether they're rocky or gaseous. But the other like really interesting area of exoplanets is trying to characterize the atmospheres of these planets. And there's different ways to do that, but one of the ways is if the planet goes in front of the star again, then the starlight is like filtering through the planet atmosphere. And then we can measure what wavelengths are being absorbed. So what molecules or elements are actually present in the atmosphere of the planet. So it's almost like getting like a chemical fingerprint for the exoplanet. And then ultimately what we want to do is try to search for biosignatures.
Yeah.
So are there things in the presence of the atmosphere of this planet that could ultimately indicate life?
Well, there's so much to make sense of to figure out if there's another planet that exists. How have you seen technology change over, let's say, the past decade, and how has that helped influence your work?
Yeah, I mean, there has been a big push from, I'd say, from CPU to GPU, and that allows you to really speed up your computational power. And in the future, maybe we will see a switch to quantum computing, possibly.
Oh, yes.
And in which case, then we could really accelerate stuff. And for example, I'm interested in 3D magneto-hydrodynamical simulations. So we're doing like nonlinear MHD equations, and that's something that could possibly really be sped up much further. Right now, we have to parameterize some of the signal, but in the future, we might be able to create an entire realistic star based off of all of these. And so that's like a big way where technology is enhancing its significantly improving the realism of the simulations that we have, as well as really pushing the boundaries of what the instruments can do. I mean, when we are trying to measure an Earth-like planet,
Yeah.
you need, it's 10 centimeters per second signal, but that is like a fraction of like it's 1/10,000th of like an atom, or 1/10,000th of a pixel on your detector. Like you're talking about a fraction of a silicon atom here. So you have to be incredibly precise with our instrumentation. So the technology is really important for like making sure that we push that side of things forward.
It's interesting you mentioned quantum computing, because I never really understood the use case for it. But with all the data and information that you're collecting, I guess quantum can help speed up that process of you being able to process the data and make sense of it to help us understand the work you're doing quicker. What are some of the pushbacks in technology? What would you say we're still not quite there yet? And I can't wait for when we do get there, that technology still needs to advance in that space to really push your work forward.
Yeah, I would say that like at the moment we still tend to use machine learning or AI as a bit of a black box. And so we don't necessarily, there's often a little bit of a disconnect between the physics and the solution that, like, say, if you did go through a machine learning framework, you might be able to push a bit further in terms of precision, but you don't necessarily understand the nature of the signal that you're removing. And so I'd say there's a little bit of a disconnect between like understanding the actual physics at play and trying to push the precision levels.
Okay, awesome. So as much as it's advanced, there's still opportunity for growth.
Yes, definitely.
So you've chosen the UK, and more specifically University of Warwick, to undertake your studies. Why is that, and what opportunities have there been for you to go ahead and succeed in your research?
I would say one of the biggest drivers was actually this UKRI Future Leaders Fellowship. It's an amazing opportunity to be able to actually have the funding to be able to support a whole group. So it's not just, okay, I got a position to be a lecturer somewhere, which is great, but I got a position to be able to be a group leader and to be able to hire postdoctoral researchers that come and help me advance these questions, and to have the funding to be able to do that was really key. And there's also flexibility that comes with that, and security. And the University of Warwick was a great place for a couple of reasons. One, they promised a proleptic appointment because of the Future Leaders Fellowship. So straight away I was permanent, which gave me that job security, which was really crucial. And allows you just that freedom and flexibility to be able to explore those really hard questions. And sometimes you need that when you don't know, like when it's big risk, you want to be able to have that opportunity. And then on the other hand, the University of Warwick is like world leading in exoplanets. We're one of the biggest exoplanet groups in the world, actually. And they're doing amazing work here from all sorts of different areas of exoplanets. And so that was a really nice fit. But then also, it's just a really nice group of people. Like I knew some of them coming in, and now I've been here for 5 years, and it's just a really welcoming and inclusive environment. And so that's one of the reasons why I'm happy to stay.
So it seems as though funding opportunity, as well as being at a university which is world leading, and also just a great group of people to work with, which I think is really important.
Yeah, definitely. And straight away, the university backed my research area, and I was able to join collaborations that wouldn't have been possible. For example, I'm part of the terror hunting experiment, which is a 10-year survey to try to find an Earth analog. And we have like a big collaboration worldwide. And so there's people in the Netherlands, there's people in Spain, there's people in the US, and then there's like 5 different institutes here in the UK. And so we were able to like buy into that and have access to this incredible data set coming up.
Wow.
So that was like another bonus for coming here.
So it seems as though University of Warwick loves international collaborations and supporting you in other sort of adventures which are related to your work, which is good to see.
Yeah, definitely.
So what has been your most exciting or surprising moment in your research so far?
Yeah, that's a good question. I'd say one of the most exciting and also a little bit unexpected at the time came from I had a secondment at the University of Geneva, and the University of Geneva is really observationally focused. So they're really a lot based on the empirical side. And at the time, I was really simulation based. I was
Hmm.
really working on those like model stars. And we were trying to find a way to empirically validate the simulations. And so say like, okay, do they actually match real world data? And then we realized we could use those transiting planets that we were talking about, like when the planet goes in front of the star and
Mm.
blocks some of the light. And so if we observe the star all by itself, and then we observe the star when there's a planet in front, and if we subtract those two,
Yeah.
then we can isolate the starlight behind the planet, which means we can spatially resolve the star. And normally we can only resolve the details of a star like our sun, where we can actually like take a picture of it and see individual
Yeah.
ones.
Mm.
Otherwise, for other stars, they're like a point source. And this gave us a way to be able to spatially resolve it. And originally, we were just thinking about it from trying to validate these simulations.
Mm.
But then we realized, oh, actually, because the star is rotating, then we can learn a bit about how the planet's orbital alignment is relative to the stellar spin axis. So in our solar system, they're all aligned because we think they've formed in like a calm way out of the same sort of gas bubble per
Hmm.
se. And then, so everything is kind of aligned in a nice, smooth way. But in other solar systems, we find that there was maybe some dynamical interaction and that there was maybe some violent history and they can be misaligned. And this offered us another tool to be able to probe that.
Mm.
And so then all of a sudden it became a more powerful technique. And now, even here, I had some master's students at the University of Warwick looking at that technique and saying, okay, how can we use this and look at chromatic dependencies? And by that, I mean like the color dependence of our observations.
Okay.
And that allows us to then probe the atmospheres of the planet. And so it was this like one tool that we thought, oh, okay, we can use this to just validate the simulations. And then over the years, it has become this tool where we can probe the dynamical histories of planets. And now here at the University of Warwick, we're also using it to probe the atmospheres of the planets as well.
So I guess this tool, you just saw it in one facet, but then being able to understand how to use the tool for multiple facets provides a more holistic understanding of potentially development of the star, the relationship of the star and the planet in question. And you even mentioned things like color difference, which is not something that I would have thought of because we thought about the wobble, sort of the pull between the two planets, how much light density you're blocking, but even color is
Yeah.
impacted.
Yeah, even color, because what we can do when we're observing stars, we use a spectrograph. Well, we can use a spectrograph, which is basically just like a prism
Mm.
that breaks it up into like a rainbow so you can see the different colors. And then if you are an element in a particular wavelength region, then if it's present in the planet, it'll be absorbing there.
All
And
right.
so like if you're observing in a particular color,
Mm-hmm.
then you can see like, okay, what is the size of the planet in that color? And then change to a different color and say, what's the size of the planet there?
Wow.
And that helps you learn about what elements are present in the atmosphere of the planet.
So looking through different colors impacts the observations that you see. Why would why is there a difference between observing in red and observing in green, let's say?
Yeah, so it's because of what the composition is of the atmosphere of the planet. So if the
Okay.
planet had no atmosphere whatsoever, then there would be no color dependence.
Okay.
But if the planet has an atmosphere, then it might be observing it at a particular wavelength. Because, for example, if it has water, that will appear at a particular wavelength, and wavelength is connected to color.
Okay.
And so, like for example, a lot of the biosignatures are actually at redder wavelengths.
Mm.
So it's one of the pushes for like why we want to try to observe in the infrared or the near infrared to try to observe those molecules that are present at those wavelengths and those colors.
Yeah, I think to contextualize it, I just see it as like you put on glasses and then you get like a red film to see like to see if things look different, or you put on a green film to see if things look different. And I think that's what you'd apply in essence to a telescope. I assume putting those different color lenses to see, oh, wow, I didn't see this in the red light, but I see this in the green light and stuff, which is incredibly fascinating stuff.
Yeah, essentially that's what we're doing with the spectrograph or the prism is we're just separating the wavelengths and so isolating different colors. Yeah, which is a similar concept to thinking of, okay, we're going to look in this particular filter at this
Oh,
time.
there's so much. Well, thank you very much, Dr. Heather. I've learnt so much about exoplanets. I think I'm incredibly fascinated by the idea of viewing the solar system using different coloured lenses, the wobble effect, the blocking of the sun effect as well, which is all very incredible and cool. So yeah, that brings us to the end of our conversation exploring exoplanets. I hope you've learned as much as I have, and hopefully sparked your interest in wanting to learn more about science research, physics research. And if you want to know about funding opportunities and other incredible research that's undergoing, please make sure to head over to the UKRI website as well as the University of Warwick.